So hello guys, myself Lovepreet Singh with my team members Taha and Vaibhav. So here we are going to present the model to predict patient state using biological census data. So first things first, talking about the data set. So in our data set, we have 2.29 million rows and we have about 12 biological sensors of which we are using the data. And about 38,000 sequences we have in the data set. Each sequence have its 60 seconds recording of different subjects, or you can say patients. We are predicting the state which can either be 0 or 1, means a patient can either be in ill state or the patient is healthy, right? So we are predicting the patient state using his or her sensors, that is biological sensors data, and that data is of 60-second recording. So talking about the data itself, here we have plotted the data. I mean, the data is uniformly distributed, as you can see, but the plot is about the average state of subject. The average state here you can see the y-axis, and this is the subject. So each subject have its unique ID. So each subject, the subject can occur multiple times in the data set. So each subject have different state, right? So we have plotted the subject versus state, and the state here is average state of that subject. So you can see the state versus subject is uniformly distributed, and the subject which have the value closest to 0 means that particular subject remain in the state 0 most of the times whenever he or she go tested through that through a hospital maybe, and those census data is fed into the data set, right? After that you can see the sensors or subjects giving value close to 1 means that particular subject remain in the state 1 most of the times. Now this is what our census data look like. Okay, so here we have plotted the average reading of the sensor at each time steps for state 0 and state 1. And here we can see that sensor has peaks and troughs throughout the 60-second. Okay, this blue line is for the state 0 and green one is for the state 1, right? So here we have plotted sensor 0 and sensor 1 only, and this is how our time data of the sensors look like. Now, before training any model, you must have an idea, complete idea about your data set distribution. So this is what our sensors distribution look like. So referring to this plot and these two plots, this is the skewness of sensors, kurtosis of sensors, and this is the distribution of sensors, the probability plot. Okay. Now, referring to these three figures, you can see first thing first, that is positive skew means tail is on the right side of the mean in the distribution. Negative means tail is on the left side in the distribution. Okay, respective to its mean. Skewness is the measurement of the asymmetry of the distribution about its mean. Okay, and these both points conclude about the skewness, what the skewness is. And kurtosis, higher value of kurtosis means greater extremities of deviation from its mean. The census distribution is not normal. You can see it's not normal, and most of the sensors have the outliers. And most of the data of sensors is clustered around zeros. Okay, big number of zeros are present in each sensor data. So we have used two things, that is Grubbs test and Z-score. So Grubbs test and Z-score determine if there are outliers. They help us to find and remove them. So after finding, we have set a critical value in the Grubbs test. So after finding the outliers, we have removed them. And now you can see most of the sensors have normal distribution. But it doesn't mean that each sensor should be used, right? Because the feature that is not useful, the training on that feature will lead to overfitting of our model. So to to make our model best fit for the known seen values, we should have the features that are useful. So we have used the MI, mutual information score, of each sensor with respect to the state So now you can see every sensor has led to very low mutual score. So one insight from this data is like we might need some set of transformed or modified features, right? So to test that, we transformed the features using maximum value of the feature in 60-second recording, the minimum, the median, the standard deviation of the feature, and the kurtosis. Feature here means the sensor's output. So we found a set of useful features. The method is defined in the report in greater detail. So after finding useful features, we found around 43 useful features, and using those features, we use the LSTM. Now the point is, why LSTM? Because the main point is our data is time series data set, right? So actually we could use RNNs also, but RNN lose previous layer information. As we know, if the data set, if the layers are large enough in the sequence, then the information which was not latest, then it will be forgotten in the next layers. So that's why simple RNNs are not good for remembering the previous layers information, due to which we have to use LSTM. We have used the bidirectional LSTM here. The bidirectional means both forward layer and backward layer will be fit into the activation function. So this is the LSTM architecture. Our input is 60 cross 43, and input layer bidirectional LSTM, and then concatenate. Then we have max pooled the data set. I mean the output of previous layer, and this is the LSTM architecture which we have used. So in a nutshell, we imported the data set. After importing, we did exploratory data analysis. We found distributions, we found the mean, standard deviation, kurtosis, due to which we found outliers. We performed grubs testing and z-score to find the outliers and removing them. Then we used mi scores to find if there is any correlation between state and sensors. Then after doing all this, we found that we have to transform the feature. Then we did the feature engineering part, which involves the transforming the features. So after transforming, we found that LSTM giving us the good accuracy. The point being, the point of using LSTM is only due to the large data set I mean large number of features, due to which we have to remember the previous layers information also. So we used LSTM. To enhance it, we used bidirectional LSTM with a particular model. So after that, we have saved the model, and now you don't have to train the model again and again. You just have to import the saved model, and you can do your predictions on the patient using its 12 sensors data, right? So that is it from our side. Thank you. And